Chapter 9: The Debates, Progress and Likely Future Paths of AI. Part 3: Progress, Priorities and Likely Future Paths for AI. As we consider the progress, priorities, and likely future paths of AI, this section is anchored by exploring a better way of measuring intelligence for AI systems, as this would be one sensible way of getting relevant feedback on the true progress that we are making in developing better AI systems, and also possibly help to direct and prioritize future AI research and engineering paths. Earlier in this chapter, I've referenced Pierios Karufi's complaint about no significant progress being made in the development of abstract algorithms that improve automatic learning techniques. He describes today's deep learning as a smart way of number crunching and manipulating huge data sets in order to classify or predict data which is driven by increased computing power and lots of data without any groundbreaking paradigm shift. In Francois Chollet's paper on the measure of intelligence, he draws special attention to the many defects of the current AI research agenda and reasons for a psychometric and ability-based assessment of AI systems, which allows for a more well-grounded, fair, and standardized comparison between not only human and machine intelligence, but any two intelligent systems. As mentioned earlier in this section, there are at least two divergent visions for intelligence, where the one sees it as the ability to execute a collection of task-specific skills, and the other as a generalized learning and skills acquisition capability. One of the current shortcomings is a focus on benchmarking intelligence by comparing the skills exhibited by AI systems and humans at specific tasks, such as video and board games. This approach is limiting and not a true reflection of intelligence, as it is not measuring the skills acquisition capability that also takes prior knowledge and experience in consideration to showcase the true generalization capability with respect to robustness, flexibility, and generality, along with the adaptability of the intelligent system. The performance evaluation of skills-based narrow AI systems is typically done via a human review, a white box analysis that inspects the implementation of the system, benchmarking against a known test set of inputs, or competition against humans or other AI systems. When considering evaluating generalization capability, it makes sense to categorize the degrees of generalization, which can include zero generalization capability with systems that are applied to tasks or applications with no novelty or uncertainty, local generalization or robustness that is displayed in systems that can, for example, handle new points from a known distribution, broad generalization or flexibility, where systems handle a broad range of tasks or applications without human intervention, or extreme generalization that is demonstrated in open-ended systems. He also differentiates between system-centric and developer-aware generalization, where the latter refers to the ability of an AI system that handles situations that both the system as well as the developer of the AI system have not seen before, whereas in the former case, it is just the system that has not encountered the new situation. Francois Chollet argues against a more universal generalization, also called universal G-factor, from a no-free lunch theorem of intelligence perspective, as all known intelligent systems, such as humans, are typically conditioned on their environment and optimized to solve their own specific problems. So universal intelligence, according to him, does not provide any shortcuts in this regard, as any two AI systems, which include human intelligence, are equivalent when their performance is averaged across every possible problem from a uniform distribution over the problem space. So all our definitions of intelligence are for all practical purposes only relevant within a human frame of reference. This goes directly opposite the viewpoints from Universal Psychometrics or Universal Intelligence by Shane Legg and Marcus Hutter that completely rejects an anthropocentric approach and aims to use a single absolute scale to measure all intelligent systems. Francois has also put forward an actionable definition of human-like or human-level general intelligence, which is based on an algorithmic information theory, a computer science extension of information theory, and focuses on skill acquisition efficiency as well as incorporating concepts such as scope, generalization difficulty, priors, and experience. In the positioning of the skills acquisition problem, an intelligent system generates a skill program to interact with a task that also has a scoring function. In his definition, he formulates intelligence as the rate at which an intelligent system converts its experience and priors or current state of information into new skills, a skills program, at useful tasks that involve adaptation and uncertainty. More intelligent systems have a higher information conversion ratio and can cover more ground in the future situation space using the same information. This measure of intelligence does not only cater for prior knowledge and experience, but also the generalization difficulty of tasks, as well as the subjective weighting and construction of the tasks involved. It is also tied to the scope of the task, treats a skill as a property of the intelligent system that generates a skill program that accounts for future uncertainty and ensures that learning and adaptation is involved in the skill acquisition process and not just curve fitting. This measure of intelligence also considers optimizing a curriculum space that consists of a sequence of interactions such as feedback between a task and an intelligent system and situations and responses between a task and a skills program over a training phase in order to improve the intelligent system skill and skill acquisition efficiency. Although information efficiency is the key focus here, one can also consider including efficiencies with respect to computation, time, risk, and energy. Francho reckons that an ideal intelligence benchmark should address its own predictiveness and validity with regards to scope, its reliability or reproducibility, the measurement of broad-ranging abilities and developer-aware generalization, the amount of experience leveraged, a comprehensive description of the set of priors being assumed, and ensuring that it can be applied to both humans and intelligent machines. By following these guidelines, he presents the abstraction and reasoning corpus (ARC) dataset to function as a benchmark that is built upon a clear set of priors designed to mirror natural human priors as far as possible. Francho proposes that ARC can be used to compare general intelligence between AI systems and humans as it measures a human-like type of general fluid intelligence, which is basic processes of mental activities such as reasoning that only minimally depend on prior learning and acculturation. ARC's training set consists of 400 tasks, whereas the evaluation set has 600 tasks, which is split up into a public evaluation set, 400 tasks, and a private evaluation set, 200 tasks. Core knowledge priors include, for example, objectiveness priors, object cohesion, object persistence, and object influence via contact, goal directness priors, numbers and counting priors, and basic geometry priors. Some of the key differences with psychometric intelligence tests, such as traditional IQ tests, include a fundamental different design, only focusing on a general form of fluid intelligence that tests reasoning and abstraction, unique tasks that are unknown to developers to assess developer-aware generalization, greater task diversity to reduce the possible hard coding of task-specific solutions, and ensuring that tasks cannot be programmatically generated, such as those from C-test, i.e. comprehension test, to help prevent reverse engineering the generative program shared across tasks. Although ARC still is work in progress and have some weaknesses, such as generalization that is not quantified, test validity that is not established, dataset size and diversity that can be increased, making the evaluation format less close-ended, and improving on the core knowledge priors, the existence of an AI system that can solve human-level ARC tasks would be a breakthrough. Francho Cholet's formal intelligence measurement framework has practical implications for both research directions towards strong AI and evaluating these types of AI systems. It also provides a quantitative mechanism to go beyond just measuring task-specific skills to evaluating and reasoning about concepts such as generalization difficulty, intelligence as skill acquisition efficiency, and control for priors and experience when evaluating intelligence. On the research front, the quantitative intelligence formula can be explicitly used as part of an objective function where the formula can be optimized to create improved intelligence systems. Instead of only measuring skill levels at individual tasks, it also supports more flexible and general-purpose capabilities by, for example, disregarding tasks that do not have a strong generalization difficulty and penalizing too much dependence on experience and priors. Another important outcome of this formalism is the emphasis on program synthesis and separating the intelligent program synthesis engine from the non-intelligent skills program that is the artifact of the intelligence process. The difference between the process and the artifact seems to be a key misunderstanding in AI research and development. This framework also endorses the development and enhancement of a curriculum by putting emphasis on improving the system's intelligence through driving towards an optimal curriculum. It also emphasizes human-like knowledge priors in evaluating intelligence. In terms of the practical consequences for evaluating strong AI systems, the intelligence measuring formalism makes quantifying generalization hardness more formal and explicit with respect to local, broad, and extreme generalization and disregarding tasks with no generalization difficulty. It proposes clear recommendations for comparing human intelligence with AI systems by ensuring that the priors and scope of tasks are shared and experience efficiency in mastering specific skill levels are evaluated in a fair fashion. As tests are being developed for tasks, it is also vital to consider the generalization hardness in order to ensure that solutions that are dependent on shortcuts do not generalize. As an example, François shares a computer vision use case of where global semantics should be the focus as opposed to a dependence on local textures. Finally, the framework also asks practical questions to help characterize the AI system in terms of scope, maximum achievable skill, priors, curricula, and skill acquisition efficiency. In the blog, The Future of Deep Learning, François Chollet describes his long-term vision for machine learning that starts by viewing models more like software programs that mirror human-like abstract mental models that have representations of themselves and their environment. The deep learning type of continuous geometric transformations of inputs can just be considered a subset or module of the AI system's capabilities, along with other more algorithmic types of software modules that are stronger with respect to generalization, formal reasoning, search, and abstraction. These models or software programs will then be able to combine multiple modules in flexible ways that have a range of capabilities where geometric modules can equip the AI system with pattern recognition and informal intuition functionality to complement the algorithmic types of modules. An early example of this is provided by DeepMind's AlphaGo system that consists of deep reinforcement learning, geometric AI module, as well as Monte Carlo search, symbolic AI module, components to solve the problem of playing Go at expert level without human knowledge. Instead of having many human-driven design decisions and software engineering to construct the system and its modules, as was done with AlphaGo, the AI system should preferably automatically develop its task-specific models using modules from a growing global library of reusable subroutines that represent common problem-solving patterns that are continuously being updated as tasks are being solved successfully. A meta-learner that operates on a continuous basis should be capable of quickly building a task-level model across a range of tasks from this growing library of abstract routines by making module-related design choices in the modular task-level program that learns to solve a specific task on the fly. As the modular task-level program gets data and feedback from the tasks that it is working on to solve, it passes task-related data and feedback also to the meta-learner. The meta-learner helps to build an abstraction capability by pushing reusable modules to the library and fetching relevant ones for use by the modular task-level program. This continuously evolving AI system, consisting of the global library and meta-learner, would in principle be able to generate task-level programs or models that can realize human-level type of generalization on specific tasks using a rich variety of available modules and considerable experience on similar tasks. Joshua Bach also describes this meta-learner capability as a third-order type of AI that mirrors the human brain's capability to learn how to learn new things. In this framework, the first-order AI systems would be represented by classical AI from 1950 to 2013, whereas the second-order AI system are able to generate a model or program that are able to find a program that you want to develop, and where deep learning is, for example, used to approximate compositional functions within the program. An example would be to, instead of writing a program to play Go, you write a program that learns how to play Go. One of the issues with the current second-order systems is that it is thus far not general enough. An AI system, as described by Francois, would be able to both make the second-order AI system more general and also address the third-order AI system's meta-learning capability. Joshua also asks if a fourth-order AI system would involve a general theory of search. Within Francois' strong AI framework, high-level intelligent search would also be required by a meta-learner to search for the most relevant modules in the global library to be used within a modular task-level program to help solve a specific task. As a number of other AI researchers, Jan LeCun has described some obstacles to progress in AI as not having AI systems that learn and understand how the world works from a physical, digital, and people perspective, and the need to acquire some level of common sense. As a result, there is a huge amount of background knowledge that needs to be learned through observation and action. These AI systems also need to perceive the state of the world in order to make accurate predictions and do planning. It further needs to update and remember estimates of the state of the world by recalling relevant events and paying attention to important events. Very importantly, the AI systems also need to be able to reason and plan by, amongst others, predicting which sequence of actions will lead to a desired state of the world. So to have an AI system that has both intelligence and common sense would require the combination of capabilities such as perception, predictive modeling, memory, reasoning, and planning. Both Joshua Bengio and Jan LeCun believe that self-supervised learning algorithms, which generate labels from data by exposing relationships between the data's parts, to be a key component in achieving human-level intelligence. With self-supervised learning, a part of the input is used as a supervisory signal to predict the rest of the input. As humans, we learn models of the world by predicting part of the input from other parts, masked input from the visible inputs, obstructed parts from all available parts, and the future from the past. Jan LeCun emphasizes that more knowledge about the world's structure and workings can be learned through self-supervised learning compared to other methods, as it capitalizes on the unlimited data available and makes better use of the feedback that is provided by each input example. As humans, we learn mostly in this self-supervised mode via observation that does not require testing along with some interaction with the world. A key problem for self-supervised learning in AI systems is that we still do not have a practical way of representing the distribution of variables that are continuous in nature. They can only be obtained by measuring, as opposed to discrete variables that can represent uncertainty properly, as in the case with supervised learning. Jan LeCun is proposing energy-based models, EBM, that learn the mathematical elements of a dataset and try to generate similar datasets as a potential solution to the continuous distribution problem. He describes EBMs as a type of non-probabilistic graphs that capture dependencies between variables by associating scalar energy to each configuration of the variables, where inference consists of clamping the value of observed variables and finding configurations of the remaining variables that minimizes the energy, and learning consists of finding an energy function in which observed configurations of the variables are given lower energies than observed ones. Researchers at OpenAI have also made some progress towards stable and scalable training of these energy-based models that leads to improved sample quality and generalization ability compared to existing models. Some of the advantages of EBMs and iterative refinement include adaptive computation time, which allows for generating samples at low temperatures that are competitive with the ones that GANs can generate, not being restricted by generator networks that need to learn to map from a continuous space, but instead can learn to assign lower energies at disjoint regions, and built-in compositionality that allow EBMs to be combined through hierarchical models. Energy-based models can also help to address compositionality, which is one of the unsolved problems in AI research. While the brain finds it easy to learn in compositional fashion and produce new combinations from known components, this has not been the case for neural networks in general, and a key reason for why deep learning models require huge amounts of data in order to learn, have issues with transfer learning, and find it difficult to do zero and one-shot learning. As we currently do not have continuously learning AI systems that have a global library and meta-learner, today's AI systems are not able to discover and store skills or capabilities that are common across problems or tasks, and to reuse and to recombine them in an hierarchical or compositional fashion to solve new challenges. Compositionality is also a common research theme in task decomposition, hybrid AI architectures that integrate symbolic AI with deep learning, neural architecture search, transfer learning, and sub-goal discovery in reinforcement learning. There have been many approaches to compositionality, such as a divide and conquer one that decompose a problem into subtasks in such a way that existing solutions to subtasks can be combined to solve the problem, making use of symbolic AI primitives that can execute logical reasoning steps over abstract compositional representations with elements such as objects and relations, using pre-trained models as primitives in transfer learning, and integrating symbolic AI primitives with deep learning. Although neural networks such as encoder-decoder networks and generative adversarial networks consist of multiple underlying networks, they operate together more as a singular system to achieve a specific outcome as opposed to a distributed model that assigns tasks to specialized networks. Compositional learning is also different from ensemble type of machine learning, as compositional systems have specialized models working on different tasks and in a specific context with one another. Compositional learning also involves much more than just making algorithm choices and preparing the data as the appropriate models should be selected for the various tasks, and there are many ways the relationships between each of the specialized modules within a compositional system can be organized in a context-dependent fashion. A number of modular network architectures have been manually designed, such as the one that makes use of a training algorithm that flexibly chooses neural network modules based on the data to be processed, handling the model choice as a latent variable in a probabilistic model, and learns the decomposition and module parameters in an end-to-end fashion. An example of a manually handcrafted compositional system that incorporates both symbolic AI and machine learning components are the Deep Symbolic Reinforcement Learning Hybrid AI system constructed by Marta Garnello and colleagues, where the end-to-end reinforcement learning architecture consists of a neural network backend that learns to map raw sensor data into a symbolic representation and a symbolic front-end that maps the symbolic representation to actions. In the paper Reconciling Deep Learning with Symbolic Artificial Intelligence, Representing Objects and Relations, Marta Garnello and Mary Shanahan from Google DeepMind showcase how specific aspects of symbolic AI can fit within a deep learning framework and how a deep learning network can be trained to acquire and use compositional representations with objects and relations as elements. However, we are still far from an adequate synthesis, as such a compositional system would ensure that representations are learned from data with minimal priors and consist of elements such as variables, quantifiers, objects, and relations. Such a system would ideally not be constrained by the formal logic rules, but support arbitrarily long sequences of inference steps using all of the above-mentioned elements and able to learn various inference forms. As mentioned in the previous section, instead of handcrafted systems, some progress has been made in neural architecture search, where a search strategy selects an architecture from a predefined search space, then passes the architecture to a performance estimation strategy, which returns the estimated performance of the selected architecture to the search strategy. Mattia Ferrini has also proposed a high-level compositionality framework that can integrate sub-goal discovery in neural architecture search, align research on sub-goal discovery with existing research on compositionality, use attention mechanisms to incentivize compositionality, develop a bridge between transfer learning and neural architecture search, and reconcile deep learning with symbolic AI by ensuring that symbolic primitives are available to neural architecture search frameworks. Microsoft Research published findings around the relationship between accuracy and locality and compositionality that aims to provide researchers with a more rigorous approach to zero-shot learning. In a paper Learning Compositional Representations for a Few-Shot Recognition by Carnegie Mellon University researchers, an attribute-based regularization technique is introduced that allows the learned representation to be decomposable into parts and show that they require fewer examples to learn classifiers for new categories on certain datasets. For a human-object interaction detection use case, a deep visual compositional learning framework was developed to localize and infer relationships between humans and objects in images that achieve state-of-the-art results on specific datasets. In his paper, The Next Decade in AI, 4 Steps Towards Robust Artificial Intelligence, Gary Marcus proposed a hybrid knowledge-driven, reasoning-based approach that is built on cognitive models as a substrate to enable a richer, more robust AI than is currently possible. He defines robust AI as intelligence that can be counted on to apply what it knows to a wide range of problems in a systematic and reliable way, synthesizing knowledge from a variety of sources such that it can reason flexibly and dynamically about the world, transferring what it learns in one context to another in the way that we would expect of an ordinary adult. Gary's 4 steps involve a hybrid architecture, large-scale knowledge, reasoning, and cognitive models. Symbolic operations over variables offer a well-tested solution that provides the backbone for the world's software, with every program dealing with variables, instances, bindings that tie variables to instances and operations. It only lacks a satisfactory framework for learning such as that provided by deep learning. Hybrid architectures are typically effective, such as Google Search, that uses a mix of deep learning and symbol manipulation operations. Google Knowledge Graph, that uses classic symbolic graph structures to represent knowledge, along with tools such as BERT and RankBrain. AlphaGo, that uses deep reinforcement learning and Monte Carlo tree search. And OpenAI's Rubik Solver, that uses deep reinforcement learning and a symbolic algorithm for solving cognitive aspects. Also, determining whether a given system is a hybrid system is not always straightforward. Gary argues that the common objections to hybrid models and symbol manipulation can be countered. Although no neural mechanism has yet been identified to support symbol manipulation, it does not mean that it will not happen in the future and does not tell us anything yet, as we don't have a detailed understanding of how world-class chess playing is implemented in the brain. We do have psychological evidence that symbol manipulation is instantiated in the brain. Even if the brain does not use symbol manipulation on a neural mechanism level, AI can still make use of symbol manipulation. Hybrid AI systems can also scale, and we currently have examples that work well. A robust hybrid AI system also requires large-scale knowledge, of which some is abstract and causal in nature. Some considerations include that most knowledge is likely to be learned. A large fraction of knowledge that is required would be external and cultural in nature and symbolically represented. Rules and exceptions must coexist. A significant fraction of knowledge would be causal and able to support counterfactuals. Lots of abstract knowledge would be difficult to obtain via web scraping. Relevant knowledge would need to be very broad in scope. Putting knowledge into practice is hard, and a robust AI should include some innate prior human knowledge. A robust hybrid AI system should also be able to reason. Gary reckons that the best case for reasoning engines in the classical mold comes from the sort of inference that psych can perform in optimal circumstances. as an AI project launched in 1984 that aims to assemble a comprehensive ontology and knowledge base that covers basic concepts and rules of how the world works. Psych is offered by PsyCorp as an enterprise-proven knowledge representation and reasoning platform with three components: a knowledge base, what Psych knows; inference engines, how Psych reasons over what it knows; and intelligent data selection, augmenting the knowledge base by connecting to data. Psych combines these components to generate insights in the form of actionable output. Gary's observation about Psych includes that the approach would not be doable without considerable use of operations over variables, structured representations, and records for individuals. The rich cognitive models and knowledge are shown to be of great value. It would be considered a significant breakthrough to have a system that can automatically generate the Psych's representations, and having the correct information accessible in the context of real-world inference might turn out to be the actual barrier and not necessarily reasoning as such. Gary makes two conjectures about the key role of cognitive models as part of a robust hybrid AI system. It must have the capacity to induce and represent rich cognitive models, and these cognitive models cannot be constructed in an acceptable automated fashion without rich prior knowledge, advanced techniques for reasoning, and a hybrid architecture. He also emphasizes the need for hybrid AI systems that include mechanisms for spatial, physical, psychological, temporal, and causal reasoning, and states that most current neural networks lack explicit mechanisms for these forms of reasoning and does not have natural ways of representing and reasoning over such domains. In a recent interview with Jeff Hinton, he claims that deep learning is going to be able to do everything, but there's going to have to be quite a few conceptual breakthroughs. We also need a massive increase in scale. He argues that we need breakthroughs in how big vectors of neural activity can implement something like reason. We also need larger neural networks and more data. He specifically compares the human brain with its 100 trillion parameters to a big neural network model like GPT-3 with its 175 billion parameters, which is 1,000 times smaller. Jeff reckons that common sense reasoning and motor control are some of the big-ticket research items to tackle. Jeff thinks that the brain is neither manipulating representations of pixels or symbols, but big vectors of neural activity. Although a symbolic approach has its merits, it only exists in the external world and is not something that happens inside the brain. As convolutional neural networks do not recognize objects in the same way humans do, we use coordinate frames and has some limitations to easily generalize to new viewpoints. Jeff has proposed the idea of capsules that represent the segments of a given image using a group of neurons that learns to represent a familiar shape or part and then use these learned sub-representations to identify the image. In the latest version of a capsule, it has a logistic unit that represents whether the shape exists in the current image, a matrix that represents the geometrical relationship between the shape and the camera, which is called a pose, and a vector that represents properties such as deformation, velocity, and color. This unsupervised capsule autoencoder network can reason about objects using the geometric relationships between parts, which is robust to viewpoint changes. The capsule network has a part capsule autoencoder that segments the image input into parts and their poses, and uses the poses to reconstruct the image by suitably arranging the learned templates. It also has an object capsule autoencoder that organizes discovered parts and their poses into a smaller set of objects, which is then used to reconstruct the part poses using a separate mixture of predictions for each part. This new method for representing learning uses structured decoder networks to train the encoder network to segment an image into parts and their poses, and uses another encoder network to compose the parts into coherent objects. The capsule network has achieved state-of-the-art results for unsupervised classification on SVHN 55% and MNIST 98.7%. As there is a general consensus that AI has much to gain from the field of neuroscience and vice versa, Yoshua Bengio particularly believes there is much to learn from how consciousness and conscious processing works in the brain, and predicts that novel research will illuminate the way high-level semantic variables relate to how the brain processes information and how these variables are used in language communications. This can also lead to the development of new types of deep learning models. By combining models of grounded language learning and how the world works with the models that deal with high-level concepts, models can be created which mirror human conscious processing that implements explanations of how the world might change in a high-level representation. Joshua compares this type of model with the System 2 thinking as defined by Nobel laureate Daniel Kahneman in his book Thinking, Fast and Slow, where Daniel defines a dichotomy between two modes of thought or cognitive abilities, where System 1 represents the unconscious, intuitive, fast, instinctive, habitual, non-linguistic, and emotional part, and System 2 represents the conscious, sequential, reasoning, linguistic, slower, more deliberative, and more logical part. The rationale is that the current deep learning is fairly competent at automatic perception such as System 1, but lacks System 2 type of processing that requires more attention, effort, and concentration to perform mental activities such as decision-making, reasoning, and understanding. Joshua sets the challenge to extend deep learning to implement System 2 type of thinking. He reckons that some consciousness priors are likely needed to represent high-level concepts, and that deep learning can be used to predict the value of this prior in the high-level abstract space, similar to how deep learning is making predictions in the sensory space. In this System 2 conscious state, a few concepts can be combined to form a conscious thought. He claims that this architectural and information processing constraint corresponds to assumptions about the joint distribution between high-level concepts, and that this is consistent with a joint distribution over high-level concepts, which has the form of a sparse factor graph, i.e., where the dependencies captured by each factor of the factor graph involve only very few variables, while creating a strong dip in the overall energy function. Joshua conjectures further that the consciousness prior also makes it possible for conscious states to be mapped to natural language expressions, logic, facts, and rules, and can possibly be combined in a way to enable reasoning and understanding. An Ericsson research team has recently provided a selective overview of machine reasoning explainability and described machine reasoning as an AI field that predominantly uses symbolic methods to formalize and emulate abstract reasoning. Other machine reasoning definitions seem to have a strong symbolic AI slant, such as systems that generate conclusions from previously acquired knowledge by applying logical techniques like deduction and induction, or machine reasoning, which involves understanding and common sense, requires an ontology. The Ericsson paper defines explainable AI systems as one that produces details and reasons underlying its functioning and outputs thereof, and categorize explanations as attributive, such as feature importance association, contrastive, such as counterfactuals, and actionable, such as actual outcomes or guidelines towards a desired outcome. They also highlight explanations in machine reasoning, which includes inference-based, logic programming, constraint programming, automated theorem proving, argumentation, planning, decision theory, and symbolic reinforcement learning. Machine reasoning and explainability has been difficult for neural networks to master. The same holds for relational reasoning, which is a key aspect of intelligent behavior and can be defined as seeing meaningful patterns in information and can be done using analogy, anomaly, antinomy, and antithesis. The Google DeepMind team has demonstrated how to use relation networks, RN, as a plug-and-play module to solve problems that essentially rest on relational reasoning. In a visual question answering test using the Clever dataset, the RN augmented networks have achieved state-of-the-art superhuman performance. Other tests include complex reasoning about dynamic physical systems and a text-based question answering using the Barbie suite of tasks. The DeepMind team has also shown that by augmenting convolutional networks with RNs on curated sort of Clever dataset, the combined system has a general capacity to solve relational questions and can implicitly discover and learn to reason about entities and their relations. in another Google DeepMind paper, it was shown that neural networks can learn to perform explanatory and counterfactual reasoning, where an object-centric transformer substantially outperformed leading neurosymbolic models on two reasoning tasks that was assumed to be challenging for deep neural networks. The cleverer and cater task domains focus on spatio-temporal interactions between objects. A fully learned neural network, which uses self-attention, learned soft object-centric representations, BERT-style semi-supervised predictive losses, and the right inductive biases outperform all previous neural symbolic models on both these tasks using less than 60% of available labeled data. It specifically did well on questions that emphasize reasoning over perception and demonstrate that it can learn to reason effectively about the causal, dynamic structure of physical events. Whereas humans have knowledge about the features of their environment, that is not the case for typical reinforcement learning algorithms that assume that all actions are always available to an agent. A psychologist, James Gibson, coined the theory of affordance that states that when people look at the world, they perceive not simply objects and their relationships, but also their possibilities. For example, the bed affords the possibility of sleeping. This theory helps to explain why people can engage with new objects in an environment and generalize so easily because we recognize their affordances. A paper, What Can I Do Here? A Theory of Affordances in Reinforcement Learning, showcased the development of a theory of affordances for agents who learn and plan in Markov decision processes. They also proposed an approach to learn affordances that allows faster planning by reducing the number of actions available in any given situation and use it to estimate transition models that are simpler with improved generalization capability. In his presentation, Exponential Progress of AI, Moore's Law, Bitter Lesson, and the Future of Computation, Lex Fridman, an AI researcher at MIT and YouTube podcast host, gives his perspective on the progress of AI with consideration of Rich Sutton's The Bitter Lesson blog post discussed earlier in this chapter that emphasizes that general AI methods which leverage computation turned out to be significantly more effective than those that explored other methods, such as leveraging human domain knowledge. Lex thinks that the scientific community did not give enough credit and appreciation to some of the AI breakthroughs due to the brute force computational nature of the search and learning that was involved in achieving breakthroughs in chess, Go, computer vision, speech recognition, and natural language processing. He recommends that research papers should include a section that specifies if the AI method introduced does scale with compute. Rich did not specifically reference the role of data, as scaling of learning in most cases depends on scalability of data annotation. Moore's law, which can also be ambiguously interpreted as the exponential improvement of computational capabilities, may be observed at any abstraction level of computation when invested in, including at the deep learning or meta-learning or above levels. People like Jim Keller, previous microprocessor engineer at AMD and Apple, says that Moore's law is not yet dead, as the theoretical physics limit is not yet reached. Moore's law might also continue via global compute capacity, massively parallel computation, GPUs and application-specific integrated circuits, ASICs, computation of a different nature, such as quantum computing or neuromorphic computing with modeling spiking networks, brain-computer interfaces, and deep learning efficiency innovation. Learning and search also require some human knowledge expertise, such as hyperparameter tuning, and the better architectures and learning processes that we engineer. For example, convolutional neural networks versus feed-forward neural networks, which also sometimes require less compute, such as EfficientNet in 2020, requiring 44 times less compute to train to the level of AlexNet in 2012, whilst hardware efficiencies improved 11 times over this period. In the same paper, Measuring the Algorithmic Efficiency of Neural Networks by Danny Hernandez and Tom Brown from OpenAI, also observed that a realistic indication of AI progress should integrate measures from algorithmic and hardware efficiency, as gains from both multiply and can be on a comparable scale over meaningful time periods. Lex also asks, as evolutionary processes created the human brain, does evolution fall under search and or learning or not? Also, is human ingenuity or raw computational power, or both, more important for long-term progress of AI? He thinks that exponential improvements in AI are likely to continue and will predominantly be driven by efficiency in learning and search algorithms, especially active learning and data, whilst exponential growth in compute devices also grows. Hugo de Garis, an AI researcher in Evolvable Hardware, has listed some of the 21st century technologies and developments that can be an enabler for strong AI systems to be Moore's Law, 1 bit per atom capability, femtosecond switching, reversible computing, nanotechnology, artificial embryology, evolutionary engineering, topological quantum computing, nanotechnology impact on brain science, and artificial brains. As the premise of this book and my massive transformative purpose is on maximizing the social benefit of AI, I identify with the research priorities for a robust and beneficial artificial intelligence report by Stuart Russell, Daniel Dewey, and Max Tegmark, as communicated via the Future of Life Institute website. As we want our AI systems to be aligned with humanity's best interests at heart and for our benefit, they recommend expanded interdisciplinary research focused at ensuring that increasingly capable AI systems are robust and beneficial. In the report, they outline some short and long-term research priorities. The short-term research priorities include optimizing AI's economic impact, research in law and ethics, and computer science research for robust AI. For optimizing AI's economic impact, a range of research directions covering areas from economics and social science to politics to psychology need to be considered, such as labor market forecasting with jobs or tasks within jobs being automated, disruptions of significant parts of the economy through AI-driven predictions of human and market behaviors, policies for managing harmful effects, and improved economic measures. The spectrum of assisted, augmented, and autonomous AI systems being developed and deployed at scale, which impact consumers, producers, markets, and governance systems globally, leads to many legal and ethical questions that need to be addressed. These questions require expertise from legal experts, computer scientists, ethicists, and political scientists to cover, for example, liability and law for autonomous vehicles, machine ethics, autonomous weapons, privacy, professional ethics, and public policy. Furthermore, another important short-term research priority involves computer science research for robust AI across consumer-facing and industrial applications, as well as autonomous transport, trading systems, and weapons. The various ways in which an AI system may not execute as intended lead to different research areas for AI robustness, which include, for example, verification to answer how to prove that a system satisfies certain desired formal properties, especially in safety-critical situations. Did I build the system right? Validity to answer how to ensure that a system that meets its formal requirements doesn't have unwanted behaviors and consequences. Did I build the right system? Security to answer how to prevent intentional manipulation by unauthorized parties. Have I secured the system enough? And control to answer how to enable meaningful human control over an AI system after it begins to operate. Can I again get control of the system? From a long-term research priorities perspective, these four areas of verification, validity, security, and control will become increasingly critical and important as AI systems will likely become more capable and more deeply integrated into the fabric of society. As one of the long-term goals of many AI researchers, technology companies, and governments is to build human-level AI or strong AI that can potentially outstrip human cognitive abilities, it would be important to ensure that these AI systems that can have a tremendous impact on society is robust and beneficial for us. Stuart Russell also has a chapter in his book Human Compatible: Artificial Intelligence and the Problem of Control that is called Provable Beneficial AI, where he proposes training AI systems not on a fixed goal, but instead to accomplish our goals without the AI system necessarily knowing what the exact goals are. As also mentioned earlier in this chapter, having an explicit uncertainty about the nature of goals that the AI systems are instructed to pursue leads to a margin of safety that we need in building trustworthy, safe, and controllable AI systems. His solution builds on inverse reinforcement learning and transforms the AI incentives by ensuring that the AI system does not fully understand our goals. It will actively try to learn more about what we really want and always be open to us redirecting it or even switching it off if it comes to that scenario.